Okay. All right, let's get started. So, we're going to be talking about section 1.1, which is on polynomial curve fitting. So this is just a setting where we have some scalars, some input scalars, some output scalars, and we're going to be trying to fit a curve to that data. And the reason why we're talking about this really simple example is actually highlights one of the great aspects of this book, where which is kind of not about just introducing kind of a list of cookbook list of approaches, ways of fitting data, ways of testing this, testing that, but actually trying to say, trying to kind of fit them all into kind of a holistic approach of how to approach, regression problems here or classification problems and why we're doing the things we're doing. So I think this chapter is really useful because it highlights in kind of a simple setting many of the issues that we're going to be seeing throughout the book and dealing with in more sophisticated ways later. So it's cool for that. So let's get started. So the setting is, we have a real valued input, a real valued target, and we're going to try to predict the function that goes from the inputs to the targets. Now, one aspect that he kind of highlights in passing, talks about in passing, but I think is really important, is this notion that in this example, but I think also in real life it's very important to do this, we're going to be working with synthetically generated data first. So the idea is that we're going to have some approach, some curve fitting approach, some classification approach, and many people when they're faced with problems like that, they'll just take their technique that they want to apply and they'll just apply it to the real data, and they'll get some answer, but you will have no idea whether that answer was correct, and you won't. And maybe your package is right, but you haven't set up your data correctly. Or vice versa, or you've done both incorrectly. Some number will come out, and it's often not clear that you've executed the procedure incorrectly. And so it's really, really important whenever you're doing kind of data analysis technique, when you're applying data analysis techniques or running a new procedure, to run it on synthetic data first, where you know what the answer is, and to just make sure that every aspect of your pipeline, data preparation, all the way through to the data analysis, data reporting, all of that is working properly. And the way to do that is to generate ground truth data, and that's he calls it synthetically generated data. In our case, it's going to be the data is going to be generated from sine to pi of x. So we know what the true function is that generates the data, and we're going to try to see how well we do in comparison to that. So it's really important. This notion of synthetically generated data is really important, really useful, and should always be used when you're doing data analysis. I think as much as possible. It's essentially how you debug kind of data analysis pipelines. Okay, so let's get going. Okay, so now we've got a training set. So we've observed these scalars, at n different values. So here we are packed into a vector, and now we observe the target values, and we're trying to determine the function. We're going to pretend we don't know that it's sine 2 pi of x, and we're going to try to go from fit some function that takes from the input to the output. So let's kind of have a look. I think there's here's an example of some x's and some y's and some targets. Okay. So now, so how did we actually get these target values? Well, it said we first compute the corresponding value of the function sine 2 pi of x. That was our ground truth, and then we added some small amount of noise. And this is kind of capturing the common situation where our data for regression or kind of learning to be possible, you have to kind of assume there is some underlying structure. So we're going to assume that the data has this underlying regularity. But we don't observe the regularity directly. We observe it after it's corrupted by some noise. Now, sometimes this noise is actually due to a physical process, or maybe there's quantum mechanical noise that you can't actually avoid. But usually this noise is coming from, and it's great that he highlights this, variability that are themselves unobserved. So for example, let's assume that you're trying to fit the heights of people as a function of their gender and their age. Now, obviously, there's going to be some trend. There's going to be some, you're going to be able to fit some function because certainly height does vary with gender and age. But there's going to be other factors you're not taking into account. So, for example, maybe people's diet or their genetic background, things like this, that are going to determine their height. their environmental experience. That can be an important factor as well. How their environment growing up. But your model isn't going to capture that, and that's just going to show up as noise. So it's going to be some variability around the predictions you can make using the factors that you've included. So in this case, height and age. So the main point is that when we say noise, it doesn't mean that there's actually like some underlying physical noise process that's added. It's just taking into account the factors that we haven't included, the important factors that we haven't included, we can't include, we just don't know about. In addition to those unavoidable, let's say, quantum mechanical noise or whatever it is. So I think this is an important point, like where this noise comes from. It's not just randomness in the environment, it's just actually often reflects our lack of knowledge about the other factors that influence the variable we're trying to predict. So that now we come to an important point where when we've got a training set, the point isn't to fit the data on the training set. The point is always to make predictions for some new value. So, we use a training set to kind of get a good function that fits that data, but then the point is always to predict a new value. Given a new value, predict the target for that value. And for us, in our particular case, it's going to be implicitly trying to discover the underlying function sine 2 pi of x. And this is a tough problem, right? Because this is this function is in some sense infinite dimensional, and we're trying to we have kind of a finite number of samples of it. So we're trying to kind of generalize from a finite number of samples to this to a potentially much larger object. And the question is how to do this. And and that's that process is going to kind of have some uncertainty associated with it, and there's going to be some often some cost with getting the answers wrong. And so we have some tools that we're going to be discussing later in the chapter and throughout the book that allow us to come up with estimates of, for example, the functions that we're fitting that leverage our knowledge of the cost of errors, and also allow us to kind of reason about our uncertainty in kind of a principled way. So that's probability theory and decision theory, which we're going to touch on later in this chapter, and then we'll discuss more later on in the book in depth. All right, so now let's get on to actually trying to fit this data. So again, this is often you're going to have to make a choice. So you have some data set, you have to make a choice of how you're going to fit that data. One of the ways of doing so is with what's called with these parametric models, and one of those parametric models is this polynomial model. So it says this polynomial model models the targets as a polynomial function of the input value. So we've got a constant term, a linear term, a squared term, all the way up to an order m term. So there's an mth order polynomial. So we say here. And we're going to try to fit, the unknowns for us are going to be these coefficients w. So we're going to use the training data to hopefully get us good values of w, and good values are going to be judged by not only how they fit the training data, but somehow, and we'll see how well they allow us to generalize to unseen data. So that's what this is about. One important point, again, that he mentions in passing, but it's again a very useful concept and a very useful technique, is that if you looked at this model is nonlinear in x. So we have powers of x, but it's linear in the parameters we care about. So if I give you, the idea is that I can give you an input value x, and now you can create a new feature which is that value squared, and you can create a third feature which is that value cubed. So essentially you can bring in the power of a nonlinear model by creating these nonlinear features, which are, once you're given the input, those features are determined, and then you try to find a linear combination of those features. So in a sense, you're able to use linear techniques while leveraging the power of nonlinear features, and that's, I think, a really powerful idea. I believe it's called like feature augmentation, something like that. And obviously you're not restricted to using powers of your input. You can do, if you somehow had a brainstorm, you could put in sine of x, or sine whatever, a trigonometric function, and then you would find that you could actually fit this particular data set really well. Usually, you won't know what features you have to use, and so polynomials are sometimes not a bad guess. But the main point is you can bring in nonlinear features, and then find a linear weighting of those. And since the only unknown for you will be those linear weightings, you effectively have a linear model which are easier to learn, easier to talk about, etc., etc. So this is the notion of linear models, and we're going to be talking about them later in chapters 3 and 4. Okay, so now how are we going to determine these weights, right? We need to figure out these weights. The question is, how do we determine those? And let me actually move this to the side, so it's, yeah, there we go. How are we going to determine those weights? Okay, so one reasonable way, and actually even later in this chapter we'll see how we can kind of justify this, but it doesn't seem unreasonable to start, is to determine the weights by how well a given function of it, the function we have, this polynomial function, actually predicts the training data that we have. So what we're doing here is we're looking at, for every target value, we're looking at its predicted value, and now we're going to be squaring that difference. And this square difference is really useful because it doesn't care what the sign of the difference is. It'll be 0 only if and only if our function matches the data point exactly, otherwise it'll be non-zero, and the larger the difference gets, the bigger this error term. And then we're just summing those up for each one of our data points. And then finally, we're doing this 1 over half, term. That's just for convenience. And basically, it's because when we're trying to, in our particular case, when we're trying to figure out the optimal W, what we'll do is we'll take a derivative of this with respect to W, and this power of 2 will cancel this 1 over 2, so we won't have these scalar coefficients hanging around that we just normally don't care about. So that's basically why we do it. That's what he means by the later convenience. Okay, so that's our error function. Here is again the picture of what that would look like. So for every data point that you have, you look at this deviation, you square it, you add up all the contributions, and then you divide that by 2, and that is your error. And you try to minimize that. The point is to find you're trying to find a W, and every time you choose a different W, this red curve will change. Maybe it'll go from this to I don't know, like to something like that, and you just measure its differences at the data points and sum of those differences. So now the question is, well, how do we find this W? As I kind of alluded to earlier, what we can do is we can just take this ends up being a linear function. So this is a quadratic function of W. So you can see these W's are here. They're going to factor into Y, and then we're going to square them. So we're going to get something that's quadratic in the W's. So when we take the derivative, we'll get something that's linear in the W's, and it'll have a unique solution, and that's how we pick it. So we essentially just minimize the error function, and for our particular error function, that minimization we can do in closed form, give us a unique solution. Very convenient, one of the nice properties and often motivations of using quadratic errors. And so once we've got that W, often we'll denote this our estimate of the parameters with a star, or the unique solution W star. Now we look at what this object is. So now for every value of the input X, we can actually compute our prediction Y of X W star. So this is the function that we will have learned. Okay, so now you give me any X, and I can plot essentially a continuous curve for any given all the values of X. All right. Now the next aspect is, remember we said, okay, look, we have a polynomial of order m. The question is, how do you pick m, right? If m is 0, well, we just have a constant. If m is 1, we have a linear, quadratic, cubic. How do we pick that? This is a very common problem, and it's also it doesn't have a perfect answer. There are kind of methods that you can use to kind of come up with an answer. We're going to talk about one here, and the method we'll talk about here is essentially one of the most common ways of dealing with this problem, by essentially looking at how well different orders generalize to unseen data. But the interesting thing of this next section is showing what happens for different orders of m. So we're going to try, m is 0 all the way to, m is 9, just for illustration purposes, and see what that does, and then how we can deal with it. So I think that the easiest thing to do at this point is to just look at the picture. So here on the left, sorry, it's cut off a little bit, but this is the linear fit. So the data points are these blue dots, and m is equal to 0 is just a constant term. So it's just going to be taking the average value. So for a squared loss, the constant fit will just take we'll find the line that is the average of the data points. And that's exactly what you see here. Now here is a linear fit, and so it seems to have found some kind of a slope in the data, so it tries to capture that slope. We increase the order further to m equals to 3. That seems to kind of capture the shape of the data, and this is jives with our understanding of the sine function, which, if you take the domain to be wide enough, has kind of a cubic shape to it. There's that. Now, interestingly, you can see for all of these cases, the data, our estimates, the red curves don't go through the data points. They're very close, and they kind of minimize this, but I'll go through it. If you make the order large enough, in this case equal to the number of data points, or 1 minus the data points minus 1, you can actually fit all of the data points exactly. So you can see it at m equals 9, you're going through every single data point exactly. And so you've actually reduced your error on the training set to 0. But you can tell that this is, in some ways, it's too wiggly, right? It seems to have kind of missed the trend to some extent and just really focus on fitting everything exactly, and thereby become very volatile and very very bouncy in between the points. So it's kind of unlikely this will generalize to a new data point. For example, if you put a new data point here, it's going to get a huge error there because it's spent all of its flexibility trying to go through every single point exactly, which has meant that it has to squish itself a little bit, and now it's going to have a huge error for the points there. So it's kind of missed, maybe it's kind of missed the forest for the trees to some extent. And this is an example of overfitting. So that's what we're going to talk about here. So indeed, so the m equals 3 polynomial gives the best fit. We obtain an excellent fit to the training data. So this is always the case. So with training data, the more complex your model is, the better you'll fit your training data. You just have more parameters. Those parameters you can tweak to fit, all little wiggles in your data. But the problem is that you will start experiencing overfitting. And the source of the overfitting is that you're essentially now using those additional parameters that your model has. You start fitting them to the noise, variability to the noise, rather than the underlying structure that you're actually interested in. So this is called overfitting, very important topic. You've probably heard about it, and one that you just need to learn to deal with, and we'll talk about how to deal with that in kind of a schematic form here, and we'll talk about it in more detail later in the section and later on in the book. Okay, once again, it's kind of worth emphasizing. So what do we care about? We don't care about the training data, right? Like I already know what the target values are on the training points. What I care about is generalizing to new data. So that's always the point. And so how can we try to measure our performance, our generalization performance? So one way to do that is by creating or having left aside some part of our data, now bringing that piece of data in, and essentially using it as a separate test set. So here, because we know how the data was produced, we can just generate another set of data points. So here we go. We're going to consider a separate test set of 100 data points using exactly the same procedure. And then what we can do is we can then try different values of m, train them on our training set, and then evaluate them on the test set. So that's kind of like measuring somehow our generalization performance. How well do we do for a given order when we train on whatever our data set is? Well, we can measure that by just having a set that we haven't used in training and evaluating performance on that. And so let's have a look what that does. And here's what that, we'll talk about what ERMS is in a second, but just think of this as kind of our measure of error. And look, there's two things to notice. So the blue here is the results of training, and m is the order of the model. And you can see that as for low orders, you get pretty poor performance. But as the order increases, the error drops until at actually 9, the error is basically completely it's reduced to 0. So that's the point where our curve goes exactly through every single point. But now what we care about is generalization performance. So first, you can see that it's always higher than the training error, just because you haven't seen that data. But more importantly, it actually will start to increase at some point. So at the value of m equals 9, you can see this test error has actually gone way up. So in some sense, you get a signal that, okay, I don't know, I can't quite tell how these guys relate to each other, but it really seems like 9 is too high of an order. And if I see something like this, I'm like, well, if their performance is all basically the same, why don't we just stick with m equals 3? Because that seems like gives the same performance. A simpler models tend to be better. So yeah, but the main point here is that using this test set, we're able to gauge a little bit what the right order of the model is in this setting for our data. So that's kind of that's essentially the kind of the meta approach of having kind of data that you've left out and evaluating the performance of your model on that data. So training on the training data, testing on this left out training set. Okay. Yeah, so that just kind of describes what we just went through. Yeah, he's going to define errors in this case by this ERMS. Why are we doing ERMS? So there's a few things going on here. First, there's a square root term going on. That allows us to measure the errors on the same scale as the data points themselves. So you can imagine, like, let's say the data, one way to see this is, let's say your data had units of meters. Well, your error term is going to be, because of the squared, it's going to be in units of meters squared. But you want to, it's useful to be able to actually compare those errors in the same units as your data points to kind of get a sense of how do they compare in terms of the size of my data, how big are they? And so that's what the square root does. Dividing by, multiplying by 2 and dividing by n, that's so you can kind of, you can compare data sets of different sizes. So, if one data set had twice as many data points, well, those errors would tend to be twice as large just because you're adding up the results over twice as many input examples. So this allows you essentially normalizes for the number of data points you have, so that you can compare different data sets on the same footing. So that's what that's about. If you actually look at the form of this, you'll see, if we kind of go back to what the error function looks like, you'll see, so we multiply by 2, so that gets rid of this, and then we divide by n, so there'll be a divide by n, and there'll be a square root. And that's basically like, it's almost like a kind of a standard deviation. So you have your data points, you try to predict, give a kind of a mean function for them, and you measure the standard deviation of the errors around that mean. So just some intuition for what this ERMS is, and we just saw, okay, that essentially, but either way, it doesn't change the point that if m is very large, the training error will go to 0. You can measure this in RMS or in the E squared, but the test error will go up. So this kind of gives you a hint as to the order of the model that you should pick for your data. Now the question is, why is it that why does a high order model do worse? And we kind of touched on it a little bit, which is, it's kind of fitting the noise, but it is kind of, I like his little discussion here about that, because you can kind of, if you view it from a certain perspective, it can kind of be a little bit odd. I'm telling you, well, the order 3 model seems like the right one. Well, the order 9 polynomial contains an order 3 polynomial, right? So for example, you could just set some of the higher order coefficients to 0, and now you've got your order 9 polynomial is actually effectively an order 3 polynomial. Another argument you might have against why the order 3 does so well is, well, the sine 2 pi of x function, if you do the Taylor series on it, it will contain terms of kind of all orders. Actually, it's all odd orders because it's an odd function, but either way, it'll have polynomials going all the way up to, basically as high an odd order as you want. So why is it that this order 9, when we have an order 9 polynomial, which will be able to include order 7, 3, 5, 3, and 1 polynomial within it, why is it that it does so poorly? And so we can so those are kind of valid questions, and we can kind of look at, to get an insight into why that's happening, we can actually look at the coefficients that we're learning. So here is the coefficients we learn when m is equal to 0. It's just a small number. M equals 1, it seems reasonable. At m equals 6, we start seeing that we're getting some quite high coefficients. At m equals 9, we've got these enormous coefficients. And essentially what's happening is you're kind of getting very large coefficients kind of battling very large positive coefficients, battling very large negative ones to come and kind of exactly balance out and meet the data points that you have. So essentially, this is kind of a signature of overfitting, that you're having these coefficients being fine-tuned, as he called it. I like that term, fine-tuned to the data by having large positive and negative values, so they'll just exactly squeeze in and fit the data points that you have. But again, we're not interested in fitting the training data. We're interested in generalizing to new data, and when that's the case, this kind of fine-tuning is something we want to avoid. So the question is, how we do that. So that's kind of exactly what it's highlighting here. Another interesting point that he discusses is that these issues of overfitting will tend to become less, will tend to diminish when we have more data. So if we kind of stick with, a maximum order of 9, well, here's kind of what it looks like with 15 data points. So you can see it still has these kind of weird wiggles, but because we're essentially constraining it with more points, it doesn't have the opportunity to kind of develop these enormous, crazy wiggles in between the data points, because essentially these data points are constraining it, saying, well, you can't swing enormously out because, well, there is a point here that's kind of constraining you. And by the time you have 100 data points, this order 9 model seems to actually capture the data really well. In some sense, you've kind of constrained it so much that it just doesn't have the opportunity to wiggle, wiggle. Although, if you then made an order 100 model, you would still find that maybe you could get these crazy wiggles. But for an order 9 model, this overfitting problem is much less. So it seems like there's kind of a balance between, and it doesn't just seem like it is the case, there's a balance between the size of your data and the model complexity. So the larger the data you have, the more complex the model you can use without running into overfitting. He actually gives a heuristic here, which, yeah, I mean, you just have to see if it holds for your particular data set. But the number of data points should be no less than some multiple 5 or 10 of the number of adaptive parameters. So if you've got, let's say you've got 10 adaptive parameters, which we do for the m equals 9 model, well, you need 100 data points. And indeed, it seems like we're not getting much overfitting in that case. But again, you have to measure the overfitting the way we've described by having a test set and holding it out. But again, it looks like in this particular setting that you've just constrained the model so much that I don't imagine this result's going to be very different if you get another 100 data points. So just you can kind of eyeball it sometimes. Now, the question is kind of, what aspect of the fitting procedure produces this kind of overfitting? And as we'll discuss in subsequent sections, what we've done here is an example of maximum likelihood estimations. That energy model corresponds to the negative log likelihood, and we'll discuss what that means later. And maximum likelihood approaches will just tend to overfit. And there are there's the other approach, which is going to be the focus of the book, which is kind of Bayesian approaches, which avoid this problem by essentially having a prior, by saying that the weights, for example, can't be so large. And if you do that properly, then you can often avoid some of these overfitting issues. Now they bring with them their own issues of how do you pick priors, etc. But at least in principle, they provide a way of in kind of a principled way of avoiding overfitting. If you can kind of state your model correctly and integrate out over the parameters that you don't care about, you can avoid overfitting with Bayesian approaches, and we'll see more of this as we go. Okay, so we saw that. Okay, so we saw that the problem was, our model was getting really complicated, and getting these kind of very large values of the coefficients. So, what if we tried to kind of reduce this, kind of penalize the size of those coefficients? So instead of kind of picking, let's say, the order of the model, which can be kind of, maybe it's going to be a little bit annoying having to go, pick exactly what order it is, we'll allow the model to be, let's say, of order 9, but we'll actually put a penalty on having large coefficients. And this is an example of what's called regularization. We're trying to kind of regularize, penalize the size of the coefficients to control the complexity of our model. And here is one of the simplest kind of way of doing that is this what's called the L2 norm, or the sum of squares, and which is this particular term here. And so the idea there is that you're going to try to fit the data. So this is your goodness of fit term, but then you're going to also try to minimize the size of those coefficients. And the hope is, and this parameter lambda is now controlling the complexity of your model. So if you set your lambda to 0, well, you're back in the case that you were before, and you're going to have your order 9 model that's going to, have these wild swings in it. But if you set the lambda very, very high, well, the coefficients are going to go to 0 because it's essentially not worth it to fit anything, because you'll be penalized too much. But in between, there'll be kind of a sweet spot where the coefficients will be kind of just large enough that they can fit the data, but also, hopefully not overfit, so not swing around too much. So this kind of lambda parameter now gives you kind of a continuous control over the model complexity. And yeah, here's kind of a minor technical point that sometimes the constant term is omitted from regularization, or it's regularized independently, because it just determines the offset of the data, and often that like the size of that offset is not something you necessarily want to penalize directly. It just has to do with the nature of your data set. So you might not want to include it into the regularization. A couple of just terminology points here. So the effect of, as we discussed, these regularization is going to reduce the size of your parameters. And actually, if you work out what it does in many of these models, you'll find that it is indeed a shrinkage of the value. So you will take like let's say your maximum likelihood estimate, and it will actually it will scale it down by some amount. So that's why they're often called shrinkage methods. And this particular form of regularization is often called ridge regression. So you'll hear these all the time. They all just mean this exact same thing. So you're just regularizing your model by a W squared term. It's very simple, a very simple procedure. In neural networks, this will also be called weight decay. Again, because you're shrinking those weights, these will be the weights of the strength of connections, the weights between different neurons. And when you regularize, when you shrink those weights, it's kind of like decaying those values from their maximum likelihood estimates. Also, there are when you do this kind of dynamically, there will be when you look at the dynamics of synapses of those strengths, when you have regularization like this, that can actually manifest in those dynamics as a decay term on the weights. So it'll be the weights will be driven by their inputs and the targets they're trying to match, but there'll be kind of a background decay in their values that's trying to avoid having very large weights, and kind of essentially making regularization happen. So that's, anyway, just some terminology. These are all it's all just this, so not to get confused by it. So now let's look at what regularization actually does. So here's kind of what we talked about. So we're going to talk about in terms of the ln of the natural logarithm of lambda. Now, when there's no regularization, lambda is 0. Ln lambda is minus infinity, and we're exactly in the situation we were before. So these are the same weights that we saw when we just fit an m=9 model. But as we increase the regularization, so now it's minus 18. Now the weights start. We have an order 9 model, but these weights aren't enormous. So it's kind of a different way of actually controlling the model complexity. So before we controlled it by just having max topping out the model at 3 coefficients. Whereas now we're allowing all these coefficients, but we're saying, look, the coefficients themselves can't get too large. So it's a different approach to controlling the complexity of the model. Here we've really cranked up the regularization. These weights are essentially 0. So I think there's a picture of that. Here we go. Yeah, here's a picture of that right here. So this is an intermediate value of regularization. So again, here's the true function. Here is our fit. And again, remember, this is an order 9 model, but with some regularization. And now it's actually, tended to fit it pretty well. And if we crank up the regularization even further, well, now there's no wiggle room in the weights. So the weights are essentially around 0, and you fit the data like that. So you kind of are now approaching that constant model. Although, again, technically it's not actually constant because you have non-zero coefficients for all the orders. So you're getting the same effect, but in a different way. Rather than limiting the order of your model, limiting the size of the coefficients. So that's pretty cool. And we can then, just like we did before with the model order, we can just look at the training and test sets, and now you get these smooth curves, which is really nice. Telling you, okay, what value of lambda to use. So, and it looks like, we would pick the one where, the test error is lowest, and it looks like it's about here. So probably even less regularization than what we have in this particular figure. But that's essentially how you would often do it in practice. So you would try different values of lambda, compute the test error, and then often if you actually want to report, because you've used this to determine your value of your regularization parameter, you want to report the performance using another data set and another part of the data that you've held out. Kind of I think it's called a validation set, or vice versa. I always get these names mixed up. Yeah, so I'm just kind of mentioned out here. So yeah, so this is I think in this particular section, which I think we're at the end of the section now. I think we've touched on some of the main aspects of regression problems that come up, which also will come up in classification as well. So how to pick a model, how to measure the deviation of the model from the data, that having training sets, test sets, regularizing your model, the way of controlling model complexity, and these are all kind of very important issues that we're going to discuss kind of and using more sophisticated, more principled approaches in future sections of the book. So I hope that was helpful, and I will see you next time for the next section. Thank you.